Here we are looking again at volumes of solids of revolution. This time we are going to look at another method different from the disc or washer method called shell method. Okay, so we've got this problem: find the volume of the solid formed by revolving the region in quadrant 1 under y equals 2x squared minus x cubed about the y-axis. Okay, so this is a cubic function. It has a negative leading coefficient, so I know that it looks something like this. And then let's find our x-intercepts. So I'm going to factor this. Okay, so this tells me I have a double root at 0 and I have an intercept at 2. Okay, so let's draw that. Give yourself some space horizontally to. Okay, so a little fritzy for a second. So double root at 0 and single root at, we'll say 2 is right here. And so that's coming down. Now, I don't really care about this part, but it's coming down this way. And we have an x-intercept of 0. Then it goes up, and then, well, I missed. We'll call that 2. Look at that. There's 2. Perfect. Okay, and it goes through there. And then we are taking that region. It does say bounded in quadrant 1. So we are taking this region. We are rotating it around the y-axis. So I'm going to start by reflecting. So that x-intercept over here, 2 units the other way. And it comes up and back down, something like this. Okay. Then we add the roundness. We're using some squish circles here to add some roundness. Okay, and there's some kind of, let's see. Let's draw one right through here. So something like this. Okay, if I use my 4 points that are all at the same height there. Okay, and so I can see that one slice kind of looks like lips. One slice appears to be in the shape of a washer. Okay, so let's slice that and try and label one slice. Okay, so of course the first question we ask is what's the thickness? The answer here is dy because the washers are stacked vertically. And then we want to know what the inside and outer radii are. Okay, so the inside radius is going to be, so this distance right here is our inside radius. That is the x-coordinate of this function. So the inside coordinate is, I'm just going to call that x1, which is something in terms of y. And that means I need to solve this for x in terms of y. And let's see, how do I solve for x in terms of y? Well, I don't think there's such a thing as completing the cube. So algebraically, anybody have any ideas? Nope, that won't work. Nope, that won't work. Good tries, though. Good tries. Okay, I'm just going to write it as f of y for now. All right, so this is f of y. Okay, and then the outside radius is this distance right here. So in terms of that ordered pair, the outer radius is, once again, the x-coordinate. However, it's the x-coordinate on the same curve, so it's also f of y. Okay, so we have two pretty big problems here. Our first problem is we don't have an algebraic method for solving for x in terms of y there. Okay, so even though I'm calling it f of y, I can't actually determine what f of y is. It's not a we haven't learned it, it's a there isn't one. Okay, and that would make sense because this is not a one-to-one function, so the inverse does not exist. Okay, or inverse is not a function. Okay. And the other issue is that when I do pi times big R squared minus little r squared, I'm doing a function minus itself, which is a problem because I'm going to get 0 for the area of every single slice. Okay, so womp doesn't work. We need to try another method. Okay, that's where the shell method comes from. The shell method, oh my gosh. Doing this again. Okay, the shell method says let's slice our solid differently. So I'm going to take out these radii here, and instead at any point, I'm just going to start with this point right here. Okay, for a representative slice, I'm going to take that and I'm going to slice one layer of a shell. So kind of think like like an onion if the sides weren't so much rounded, if they were kind of straight. Every slice here, okay, is like an infinitely thin, tube, okay? So if I take that slice that I just drew, okay, and let's say I cut it like right down here or anywhere, it doesn't really matter, and then I unroll it, I get a really, really infinitely thin rectangle. Now, that would be a shorter one if I were to slice somewhere in here, okay? Or it would be a very wide but short one if I sliced somewhere out here, okay? So hopefully you can kind of imagine what's happening here. But either way, we have this really thin slice, okay? So now let's think about how to label this. The height of this slice is the height of the function at any value of x, okay? So the height here is f of x. And actually, the first question I should have asked is, what is the thickness of this slice? Well, the thickness, because these are still cut perpendicular to the x-axis, the thickness of this slice, so imagine like a piece of paper rolled into a tube kind of thing, or like a soup can label. That's really what we're slicing and opening that up. That thickness is horizontal, so that thickness is dx, meaning everything's going to be in terms of x. So the height here is the function f of x, and that's going to be the height no matter which one I slice, going along this way, okay? And then the length of this rectangle, that's the circumference going around here. Okay, that's the circumference of this part. Well, circumference is 2 times pi times the radius, so 2 times pi times, in this case, the radius is x, and that's going to be x at any point, no matter where we draw, where we're slicing, that distance is x. So we now have an area function in terms of x, which is 2 times pi times x times f of x, okay? And then f of x is 2x squared minus x cubed for this one, so 2 pi x times 2x squared minus x cubed, which you can distribute, but we're not going to evaluate the whole thing. And so that tells us exactly what we need to put into our integrals to find volume. So volume is 2 pi, I'm going to leave that out as a coefficient, times x times 2x squared minus x cubed. Again, distribute if you want, doesn't matter. And then we need to figure out what our limits are. So our limits are on the original region. Let me try and clean this up a little bit because I got a lot of lines in here. Okay, it's a little bit better. All right. The limits are the smallest x value, because remember we're in terms of x because of dx. So the smallest x value on the region, which is 0, and they go all the way to this x value, the right side of the region, the original region, which is a 2. So from 0 to 2. And then we evaluate. Okay, so that's the shell method, and the shell method is useful anytime we can't use washer method. Now there are times where we have a region that can be the volume can be found in terms of or using the shell method or the washer method, and that's fine. You can use whichever one you want, but there are times where the shell method is necessary, like in this example right here. So generalizing here, our volume of a solid with the shell method, if we're rotating around the y-axis, so meaning a thickness of dx, is 2 pi times the integral from a to b of the radius, which is, if we're rotating around the y-axis, that's going to be an x, times the height, which is f of x. Okay, and if we go around the x-axis, we switch all those values. Okay, so let's do another example here. Find the volume of the figure bounded by y equals 1 over root x from x equals 1 to 4, and the x-axis, we're again rotating around the y-axis. So there's my axes. And y equals 1 over root x, at least in quadrant 1, which we do need to only go between 1 and 4, looks like this. Oh, that didn't even switch colors. Okay, OneNote's being stupid. Okay, and then from, I'm just going to say 1 is right here. So not quite drawn to scale, that's okay. So 1 is right here. and 4 is right here, okay? And then the x-axis, so we have this almost trapezoidal, just one side is curved region. We are spinning that around the y-axis. So I'm going to start by reflecting. Okay, so that line, and then go further out about right here. Okay, so there's kind of a reflection. And we're going to add some squish circles for roundness. Okay, and so this part right here, there's like a hole, like a tube cut through the middle. Then we kind of have a corner here. Okay. All right. I'm gonna shade one slice here just so it's a little easier to see. And there's the bottom of the solid. So we're looking at a slice that looks like this. Okay, once again, a slice looks like a washer with a thickness of dy. However, the problem we would run into on this one, and we do have one-to-one functions, but the problem we would run into on this one is the inside radius is 1 everywhere, but the outer radius, oh my goodness, the outer radius from a height of 0 up to a height of this point right here, which is 4 comma 1 over root 4, so 1/2, up to this point right here, the outer radius is just 4, but then the outer radius changes to be the x-coordinate of this function, and so we can't write one expression for the volume if the representative slice doesn't represent everywhere, okay? So instead, we are going to look at the shell method. So I'm just going to pick a point like right here, okay, and draw one slice this way. Again, think like a soup can label. If we take that and cut it, slice it down this way, and we open it up, we get a rectangle, okay? Then we ask what the thickness is. Well, the thickness is this way, so the thickness is, again, dx, okay? Then the height of the slice is going to be, no matter where the top of that slice is along this curve, the height is going to be f of x, which is 1 over root x, okay, or x to the negative 1/2 if you want to write it as a exponent. And then this distance here is the circumference of the slice, so 2 times pi times, and then the radius is the x-coordinate on this curve, so 2 times pi times x. And you might be saying, but hold on, it doesn't go all the way to the y-axis. Like, there's holes in between here. We don't have any slices that are between 0 and 1. It doesn't matter. That only affects our limits, okay? So we'll get to that part in a second. The radius is still the x. It's not like x plus 1 or anything like that because we're rotating around the y-axis. All right, so as a function, the area of this is 2 times pi times x times 1 over root x, or if you want to simplify, 2 times pi times root x. And then our volume is 2 pi times the integral of root x dx. And our limits are, again, the left side of the region is 1, right side of the original region is 4, so from 1 to 4. Okay? All right, the last one, I'm going to go ahead and I'll finish it and post that, but I'm going to stop with the video. If you have questions on the last example when you look at the notes in Schoology, then let me know.